Our final contributor to talk is from Matthew Lyon from the University of Manchester, who's going to talk about angular super resolution diffusion MRI with the 3D recurrent CNN, convolutional autoencoder.
Okay, hello everyone. Don't worry that there's a lot of jargon in that title. Hopefully, I'll do a good job of explaining what each of those words mean throughout the talk. If you want to learn more about this topic, once I'm done, there's a paper published under the same name that has a lot more detail in it than I could fit into this talk. So let's start off by discussing what diffusion MRI. So diffusion is simply the random motion of particles, also known as Brownian motion. And diffusion MRI is a modality of magnetic resonance imaging that measures the diffusion of water in specific directions. So diffusion MRI, or DMRI, is a widely used imaging modality, particularly in neuroimaging, because white matter has specific diffusion characteristics, which can be modeled in a DMRI acquisition, and then that information can be used to diagnose different pathologies or to track disease progression. So importantly, in a DMRI acquisition, diffusion is measured one direction at a time. So first of all, you might want to measure it in that direction, and then in that one, then that one, until eventually you build up kind of a picture of the overall diffusion profile of whatever you're measuring. So we call that formulation Q-space. So each Q-space sample is itself a three-dimensional diffusion intensity image measured in one direction. Each direction is defined by what's known as a B vector, which is simply a vector in 3D space. And the more B vectors you acquire, the higher an angular resolution you have. With a higher angular resolution, the better an ability you have to resolve the diffusion characteristics of whatever you're measuring, but at the cost of much longer acquisition time. So higher angular resolution data sets are clinically a bit prohibitive because of how long they take. So this project focuses on increasing the angular resolution, not by measuring more data Q-space samples, but instead by inferring new ones or previously unseen, given a small context data set. So we do this by, so we developed this three-dimensional recurrent convolutional neural network autoencoder. The autoencoder consists itself of an encoder and a decoder. The encoder's job is to calculate a latent representation view of the entire Q-space, given only a subsample of Q-space samples. And then this latent representation view is passed to the decoder along with some target B vectors to produce your output three-dimensional diffusion images. The encoder consists of a three-dimensional CNN, which is then connected to a three-dimensional convolutional LSTM. The convolutional LSTM is a recurrent aspect of the RCNN. So the 3D RCNN in the encoder, its job is to calculate features specific to each Q-space sample. And then this is aggregated by the three-dimensional convolutional LSTM to produce your latent representation view. That's then passed to a 3D CNN decoder along with your target B vectors to produce the output. So after developing this architecture, we trained on 27 different subjects from the Human Connectome project, along with 3 subjects for validation, and then an additional 8 for a test set, which these results are derived from. So we compared performance against a baseline of spherical harmonic interpolation, which is kind of analogous to a Fourier transform, but defined on a sphere. So it works quite well with this Q-space formulation. and additionally against a one-dimensional variant of our model to verify the effectiveness of the three-dimensional spatial convolutions that we included. So we ran a few different experiments using a few different subsampling schemes of sizes 6, 10, and 30, as well as a few different diffusion intensities or B vectors, B values, sorry, of 1,000, 2,000, and 3,000. And across all of these experiments, we found that the three-dimensional RCNN performed best or had the lowest error. And an example of that you can see from the top right-hand side of the slide, which is an axial plot of the root mean squared error in one test subject. So in addition to just inferring in the raw diffusion data, we also compared performance in a downstream analysis technique. So we chose diffusion tensor imaging because of its ubiquity in a clinical setting. It's very widely used. And in this case, we had an additional baseline of constructing this diffusion tensor imaging data from just the subsampled context data set. So that formed our main baseline. And in this case, we found that only the three-dimensional RCNN performed better than this baseline. And that's likely because DTI is, whilst it is widely used, it is quite a simple diffusion model. It's probably the first diffusion model developed for this technology. And so it's quite robust at low angular resolutions and doesn't really benefit from the higher angular resolution data sets that maybe other more advanced analysis techniques might benefit from. So to conclude, we developed a three-dimensional recurrent convolutional neural network model to perform angular super resolution in diffusion MRI data. We found that it performed best across varying different subsampling schemes and diffusion intensities. And further work will focus on looking at performance in different analysis techniques, ones that require higher angular resolution data, and then also looking at or exploring different deep learning architectures or ideas that can kind of better capture the unique geometry present in diffusion MRI. So thank you for listening.